Let's look at a couple examples in which we use Planck's formulas. They're actually quite easy to work with. They're located in the middle section of your formula sheet down at the bottom underneath the atomic physics formulas. We'll be kind of using that group of formulas over the next couple of lessons. Energy equals HF, energy equals HC over lambda. So you have a formula that will involve the frequency, you have a formula that will involve the wavelength, and H can be described in terms of joules with a unit on your data sheet. It's the second last constant you have. Or if you're given energy in electron volts, you'll use the H value in electron volts. So all you really need to do is just to make sure your units match up. Depending on whatever unit energy is or required, you use Planck's constant for that unit required. The formulas are actually quite straightforward. It's the understanding of the concept that's quite difficult. And I guess the biggest piece to try to think of when you try to picture photons and you try to picture quantum physics, it's very difficult to picture. I kind of picture a photon as just being a little blob of energy that moves along in a wave-like pattern. That's kind of what I do, and I kind of picture it as such. In our sketches that you'll see when we talk about photoelectric effect, do that as well. It really is, when you see a beam of light, what it really means is it's just not one continuous beam. It is a whole series of individual little packets, all carrying an individual little amount of energy, which corresponds to a color or wavelength of every different frequency. That's why we get the different colors. Each one of those packets carry a different energy for red than they do for blue, than they do for infrared, than they do for ultraviolet, which is why we only see that little tiny range of the spectrum. Okay, so our first example here, what is the frequency of a photon that has an energy of 2.80 electron volts? So we're talking about an individual photon, and what we want to find is its frequency given its energy equals 2.80 electron volts. Since the energy is in joules, I can get Planck's constant off my data sheet in electron volts. Planck's constant in electron volts, 4.14 times 10 to the negative 15 electron volts seconds. So if your energy is electron volts, get Planck's constant in electron volts. Don't mix and match the units. You will never get the right answer. So we're first of all going to figure out the frequency. Then from the frequency, we'll try to classify this on the spectrum based on what we know with the different frequencies. If you need to convert it to a wavelength, you could do that as well. Well, this is pretty straightforward. Energy of that photon is equal to HF, so solve for frequency. Frequency equals energy divided by Planck's constant. Put your numbers in. 2.80 electron volts divided by 4.14 times 10 to the negative 15 electron volts seconds should give here us a frequency of 6.76 times 10 to the 14 hertz. And that's right within the visible region of the spectrum. You would be able to see this photon. Now it's one individual photon. Remember, this formula is energy per photon, energy per packet, energy per quantum of light. And that's what Planck's formula is talking about. The only thing you really have to watch out for, make sure you've got the right units.